Hello everyone, I am Sayantika BHOWAL and I am a postdoc at ETH Zurich. And today in this talk, I will try to discuss altermagnetism from a different perspective, from the perspective of hidden magnetic octupolar order. So finding hidden magnetic order is always of fundamental interest in coordinate matter systems, and probably historically the first example of such hidden magnetic order is the antiferromagnetic order proposed by Neil to explain this cusp in the magnetic susceptibility of manganese oxide. Now, to describe antiferromagnetism, very often we use staggered magnetization, which is just the difference between sublattice magnetization. And while this is conceptually very intuitive, it lacks the convenience of any ferroic ordering, like magnetization in a ferromagnet or electric polarization in ferroelectrics. It also does not provide any information regarding the conjugate field that is required to form a particular magnetic domain. At the same time, it cannot distinguish between different antiferromagnets that do or do not break global time reversal symmetries. Now, magnetic dipolar term is just one term in the magnetic multipole expansion. So this is the multipole expansion for the interaction energy of an arbitrary magnetization density in presence of an applied magnetic field. Here, this first term is the usual dipolar term that describes this Zeeman splitting. Now, in an antiferromagnet, of course, we do not have any net magnetization, so this first order term does not contribute. However, we can still have, if our magnetization density has asymmetries, then we can still have some higher order magnetic multipole, which in turn can have ferrotype ordering. Indeed, in antiferromagnets, So indeed in antiferromagnets, which break both inversion and time reversal symmetries, are proposed to exhibit a linear magnetoelectric effect which describes the generation of electric polarization due to an applied magnetic field and vice versa. Now, this linear magnetoelectric effect actually can be conveniently described in terms of ferroic ordering of this second order magnetic multipole, which is the magnetoelectric multipole. So this effect has been proposed by Zyloshinsky for chromium-203, and also it was first observed in the same material. Here the response is diagonal in nature, and actually this diagonal response can be described by the diagonal elements of this magnetoelectric multipole tensor. Now, very recently there is a proposal for new type of magnetism, altermagnetism, which is the subject of this present conference, that actually preserves inversion symmetry while breaking the global time reversal symmetry. And as we heard many times in this conference, that the key feature of these altermagnets is the spin splitting without any need for spin-orbit interaction in the momentum space, which is very similar to ferromagnets, while still maintaining zero magnetization like a conventional antiferromagnetic system. And this, of course, has opened up a lot of platform for new emerging properties like spontaneous Hall effect, spin current generation, and so on. But here we want to look at this thing from a different perspective. So we ask the question in centrosymmetric altermagnets with non-relativistic spin splitting, what actually breaks the time reversal symmetry? So what is the magnetic order parameter which has ferroic ordering? Now, if we look at this magnetic multipole expansion, then we can, of course, ignore this net dipolar term because it doesn't have any net magnetization. It is also inversion symmetric, so this kills the second order term, that is the magnetoelectric multipole term, and hence the magnetic octupolar term is the lowest order symmetry allowed magnetic multipole which can have ferrotype ordering. Now here I want to point out that this feature here that we see is true for all centrosymmetric systems that break time reversal symmetry. So it is more general than altermagnets. So there are other systems as well which can have ferrotype magnetic octopole, but those are not altermagnet. So this probably answers Igor's question that why some other system which is not altermagnet still can have a magnetic octopole. Now, in this talk, actually I will focus on manganese difluoride. So here I'm talking about bulk crystal structure, so it is not monolayer. And in this case, the Mn ions are structurally equivalent. So this has already been proposed as a candidate material for altermagnet. And interestingly, this material has been studied for a long time, and it was believed to be actually a classic example of antiferromagnet with two Mn ions in the unit cell with the spin polarization along z-axis, which cancels each other, leading to zero net magnetization in the unit cell. However, here we have this fluorine environment around the Mn ions, which is inequivalent for the two Mn ions. And this makes time reversal plus translation to be not a symmetry operation of this magnetic configuration. And this broken time reversal symmetry in turn leads to this large spin splitting in the momentum space, particularly along gamma 2m. And this is, of course, occurs without spin orbit interaction. And here in this talk, I will take the example of MnF2 and try to discuss how the magnetic octupoles behave. So what is the correlation between structure and spin, and how it is related to non-relativistic spin splitting. And then I will discuss the implication of these magnetic octupoles in piezo and anti-piezo magnetic effects, as well as in magnetic Compton scattering effect, which in turn can be used for the direct detection of these magnetic octupoles. So let's start with the magnetic octupoles. So in MnF2, we did the multipole analysis within the density functional theory based framework, and here we find that there are 4 non-zero components of the magnetic octupole moment. 2 of them have ferrotype ordering, whereas the rest have antiferrotype ordering. So this O32 minus and O30 actually belong to the totally symmetric part of this octupole tensor, whereas this magnetic toroidal quadrupole moment and this moment of toroidal moment, they belong to non-symmetric part of the entire octupole tensor. Just to point out, these indices actually represent the L and M indices of spherical harmonics that are used to build up these particular octupole components. So here we see the variation of these octupole components as a function of the relative strength of the spin orbit interaction. So we see that even in absence of spin orbit interaction, the octupole moments have non-zero values. They change, their values change with the increase in spin orbit interaction, but this change is really weak for O32 minus magnetic octupole. Now, in addition to these magnetic octupoles, the MnF6 octahedra also are distorted, and they allow for ferrotype QZ square quadrupole moment as well as antiferrotype XY quadrupolar distortion represented by this Q22 minus quadrupole moment. And we also plot the band decomposed charge density for the top 2 valence bands that undergo spin splitting. And here we see that the charge density indeed has anisotropy in the XY plane consistent with this Q22 minus quadrupole moment. We look at the corresponding magnetization density and we find similar anisotropy. This is also consistent with the fact that the system has a ferrotype O32 minus octupole moment. Now we can see from this magnetization density and charge density plot that the magnetization density actually follows from the charge density. So we thought that by manipulating the charge quadrupoles, maybe it is possible to also manipulate the magnetic octupoles in the system. And with this idea, we modify the fluorine coordinate of the fluorine ions in the unit cell, keeping the crystal symmetry still the same. And indeed, this actually switches the sign of this Q22 minus quadrupole moment. This is also evident from this charge density plot. And accordingly, we see that the sign of the O32 minus octupole moment also switches. This also becomes evident from the corresponding magnetization density plot. Now, here I just want to point out that making this change actually does not changes the Q20 quadrupole moment, and accordingly we don't see any changes in the O30 octupole moment. So we see that at least the magnetic octupole moments, the sign of the magnetic octupole moments can be controlled by manipulating the fluorine environment, which is quantified by this Q22 minus quadrupole moment. Now actually this correlation between the magnetic octupoles and the corresponding quadrupole moments also become evident from this plot, where we vary the strength of the U parameter in our calculation and see how these octupoles or the quadrupole moments vary. This variation is not very strong, but we can see that their magnitudes actually increase with the decrease with the increase in the U parameter. But to have a more systematic control of the magnetic octupole, we want to see if that we can do by varying the strength of the charge quadrupole. And for this, we did constrained multipole calculation. So here we constrain the value of the charge quadrupole moment. The delta Q22 minus 0, this point here, it actually represents the actual crystal structure without constraining the quadrupole moment. So this structure has some non-zero values of quadrupole moment, but still this is without any constraint multipole calculation. Now, if we increase the value of the quadrupole moment, that is we constrain some value of the quadrupole moments, then we can see that correspondingly the magnetic octupole moment also increases. So not only the sign but also the magnitude of the magnetic octupole moment can be controlled by manipulating both sign and magnitude of this charge quadrupole moment. Now we want to see what is the effect of this manipulation in the non-relativistic spin splitting. So the representation of magnetic octupole in the K space is Kx, Ky, Mz. And from this representation itself, we can see that if we go anywhere in the Brillouin zone, if we have non-zero Kx and Ky, there will be some spin splitting. And indeed, in the band structure, if we go along 110 direction, we see spin splitting appearing even without the presence of spin-orbit interaction. Now, also evident from this representation, if we change the sign of either Kx or Ky, then the spin splitting should also reverse. And this is also we see in our band structure. So if we reverse, so if we rotate the momentum direction, so if we go along 1 minus 10 direction, then the spin splitting also switches. Now, we also check the band structure of our modified crystal structure, which has opposite sign of the magnetic octupole. And here we see that the spin splitting also switches sign. So this is expected because the magnetic octupole already has opposite sign in this case. Now, to see if the spin splitting, the amount of spin splitting can be controlled by controlling the magnitude of the O32 minus octupole. So we checked our band structure for those different values of the magnetic octupoles, and we see that the spin splitting along gamma to M direction actually increases with the increase in the value of O32 minus octupole. So not only the sign, but also the magnitude of the non-relativistic spin splitting can be controlled by controlling this particular magnetic octupole. Now, identifying these different antiferromagnetic domains with ferrotype magnetic octupole of different signs actually help us in identifying the conjugate field that is required to form that particular magnetic domain. So the conjugate field of magnetic octopole has the same symmetry as the magnetic octopole itself, because the free energy is invariant under both inversion and time reversal symmetries. So in this case, the conjugate field should be inversion symmetric and odd under magnetic field, and therefore product of stress and magnetic field is a valid choice. And indeed, for manganese difluoride, it has been shown long ago that cooling the sample below nail temperature in presence of magnetic field and stress actually generates one of the magnetic domains. Okay, so these magnetic domains are actually called piezomagnetic domains, and because of its correlation to piezomagnetic effect, which was also pointed out by Professor Cheong in one of the discussions. So let's try to see what is piezomagnetic effect and how it is correlated to magnetic octopoles. So piezomagnetic effect describes a change in the net magnetization due to an application of stress. And in MnF2, since there is no net magnetization prior to the application of stress, so application of stress in this case actually generates a net magnetization. And the symmetry allowed components of the piezomagnetic response in MnF2 are given here. So for example, if we apply stress along YZ direction, it generates a net magnetization along X direction, and so on. So by analyzing this tensorial decomposition of magnetic octopoles, which is done in this work, basically we find that there is a one-to-one correlation between the elements of this magnetic octopole tensor and the elements of the piezomagnetic response. For MnF2, we know the existing ferrotype magnetic octopole moments, and from those ferrotype magnetic octopole moments, we can describe this response that is not only allowed by symmetry but also observed in previous experiments. Now, I want to, so this has the advantage that if for any unknown system we know the magnetic non-zero components of the magnetic octopole moment, then we can predict the corresponding piezomagnetic response as well. Now, to understand how this piezomagnetic response depend on the domains and also how does it depend on the strength of the spin-orbit interaction, we did explicit density functional calculation. So here we apply a stress along XZ direction, and this generates a net moment along Y direction. And for the two domains represented here by these green and blue dots, we can see that the net moment generated is opposite for the two opposite domains, which is expected because the opposite domain has opposite sign of the magnetic octopole moment. Furthermore, if we increase the strength of the spin-orbit coupling, the net generated moment also increases in magnitude, and this is something different from the relativistic, non-relativistic spin splitting. So here the piezomagnetic response actually depends on the strength of the spin-orbit coupling. Now, in addition to ferrotype magnetic octopole, in MnF2 I mentioned before that it also has antiferrotype magnetic octopole. So those antiferrotype magnetic octopole also should lead to piezomagnetic response, but that would be a local response. So the response would be opposite for the two Mn ions, leading to cancellation of moment and net zero magnetic moment in the system. So from the existing non-zero antiferrotype magnetic octopole, we found from this one-to-one correlation that if we apply stress along XZ, so it will generate a moment along X direction. However, this moment along X has opposite signs for Mn1 and Mn2, and therefore they will cancel out. So we call this effect anti-piezomagnetic effect because it just leads to canting, so there is no net magnetization in the unit cell because of this antiferrotype magnetic octopole. But very similar to piezomagnetic response, this anti-piezomagnetic response also switches sign for the opposite magnetic domain, and also it depends on the strength of the spin-orbit interaction. Now, another important implication of magnetic octopole is in the magnetic Compton scattering experiment. So here the measured quantity is the magnetic Compton profile, which describes the projection, 1D projection of this spin polarized electron momentum density along the direction of the scattering vector. Now the magnetic Compton profile was believed to be actually 0 in all antiferromagnets because of the degenerate up and down spin polarized bands. However, in altermagnets, this is not the case. And in this case, actually, we expect a non-zero magnetic Compton profile. And indeed, this is what we find in our calculations. So here is the plot of the magnetic Compton profile as a function of momentum. And we can see that this profile is symmetric around the momentum p. It occurs even without spin-orbit interaction because of the spin splitting. And the magnitude is also much larger than what we predicted before for ferroelectric systems. Now here I want to point out that the integral of this magnetic Compton profile actually gives us the net magnetic moment in the unit cell. And here we find that this integral is 0, which is expected because the system doesn't have any net magnetization. Now it also switches sign if we go along 1, 1, 0 and 1, minus 1, 0 direction, as we can see from the plots also. And this is kind of a signature of this unconventional spin splitting. So this can be used for the experimental verification of this unconventional spin splitting driven by magnetic octupoles. And of course, for the experiments, we need a single magnetic domain. So with this, I would like to summarize. So in this talk, I showed that magnetic octupole is a very useful platform because it provides a unified framework to describe very different physical effects such as non-relativistic spin splitting, magnetic Compton scattering, piezomagnetic effect. And it has also opened up a lot of new directions that needs to be investigated, particularly for the case of manganese difluoride. There's a scope for investigating second-order magnetoelectric effects, surface magnetism, spin-phonon interaction, and hopefully this will motivate more theoretical and experimental work along this direction. So with this, I would like to thank my supervisor, Nicola, many interesting discussions with Andrea, Sophie, and Max, as well as with our experimental collaborators, Steve, John, and Urs regarding magnetic Compton scattering experiments, funding agencies, group members at ETH, and finally, I thank you all for listening.
Thank you very much.